For a moment, we're going to return back to some theory and focus on the particular problem of a non-homogeneous differential equation. So we haven't used the terminology yet, but as you might expect, when we just have x related to itself, this is a homogeneous first-order system, because x is related to itself with no extraneous or external factors. This form up here is the non-homogeneous form, because it has this x plus something else outside, external, or not belonging to the x's themselves. But you'll notice that same relationship we've seen before, where all the non-homogeneous part is adding something on the end of the existing homogeneous equation. Well, here's the theory that's going to come to our rescue in this case. So again, if we have a homogeneous case here, and if we can find a non-homogeneous solution, so this is what we call our non-homogeneous solution, and it satisfies the entire equation with the f of t, if we have that, then guess what our general solution is going to look like? It's going to be all these solutions here, which are solutions to the homogeneous case, or what we would have called yc. Here we're going to call it xc, or the general solution to the corresponding homogeneous system. And once we've found that, the effect of having this external function is to simply add one term on the end here. It could be a complicated term, but still one term on the end due to that externality, due to that non-homogeneous term. So it covers or solves the plus f of t case or issue. So it's nice. The theory here is blending with what we've seen before. We're going to find solutions to the corresponding homogeneous system. We know how those are built. Then we're going to find ways to solve for the non-homogeneous part of the solution. Then we can just add those together to create our general solution for the whole thing. So in many ways, no new theory, just new forms of that theory. As an example, if we look at this differential equation here, which is non-homogeneous, because we've added this external function here, here's our x prime equals ax plus, and notice it's a vector. At the end of the day, we have to put a vector here because everything else we're adding as vectors. What we can do with this is, if someone gave us a solution, and it shouldn't come as a huge surprise that if the non-homogeneous part has t's in it, so a polynomial, then our non-homogeneous solution will look like t's as well. Notice this little t in the exponent is equal to transpose. We'll use that sometimes, not too often. What that lets us do is take what should be a column vector and write it out with a little less space required as a row vector here. All right, so now we have a differential equation again. We have a left-hand side and we have a longer right-hand side. And what we're going to do is verify a solution. So what we're going to do is plug our solution in and see what it equals on the left-hand side and right-hand side. So on the left-hand side, we get the derivative of, here I'll write it out as a column vector, negative t and t plus 1. And take the derivative of each term individually. That gives us 1, negative 1, and 1. What does the right-hand side look like? Well, the right-hand side is our matrix 0, 1, 1, 1, 0, 1, 1, 1, 0, times, again, we're putting the solution in to the left-hand side, and we're also putting it into the right-hand side where x is. So we get t minus 1, negative t, t plus 1. But now, because it's not homogeneous, we have this extra term here. So I'll have 0, negative 2t minus 1, and 2. So the key thing is this is where we put our x, in this case the non-homogeneous part of the solution here. Where does that take us next? Well, we're going to expand this out and simplify and see what we get. We get 0, we get minus t, and we get plus t plus 1. We also get, on the next row, t minus 1 plus t plus 1. We also get t minus 1 minus t plus 0. That plus our 0 minus 2t minus 1 and 2. And now we can simplify row by row. These t's cancel, and we end up with 1 plus 0, which is just 1. These t's, t plus t minus 2t's, those cancel, and they end up with negative 1. And then we have t minus t, those cancel. We have negative 1 plus 2 is plus 1. Ah, not a coincidence because we picked the solution carefully. These two sides, the left-hand side gives us this when we simplify, right-hand side gives us this. These are equal, which means that our non-homogeneous solution that we proposed here is a solution to that full form. So x prime is equal to ax plus that f of t form. It is only a solution when we have that non-homogeneous form with this particular choice of functions here, but it works out for the equation we've shown. Last but not least, if we look at this non-homogeneous case again, and what we found was that the non-homogeneous solution was this t minus 1 minus t plus 1 column vector. What do we have to do to build the general solution? Well, we know what to do with this. We take our C1 times one solution to the corresponding homogeneous case. I'm going to write this out in the way that's sort of assumed, which is a function times a vector. We also found a second solution to the corresponding homogeneous case. So we'll have C2 times it. All these are e to the negative t, so we'll put that out front. And then we had a negative 1, 0, 1 vector. And then we could also have some combination or scalar value of this. Another e to the negative t out front, 0, 1, negative 1. And it's because it's the non-homogeneous case, we'll just tack on at the end with no coefficient, no multiplier, this solution here, t minus 1 minus t, t plus 1. And that would be our general solution. Every single solution that you can find to this system is going to be made up of this form with some combination of those three solutions plus a term to account for the non-homogeneous part. Again, very similar to what we've seen earlier in the course. Once we've found our solutions, building the general solution is straightforward. Of course, that leads us to how are we going to find these solutions, and we'll see that coming up.